Okay, hello, my name is Marcel, and as Stefan said, I'm talking about standard object out. After about 3 decades in industry, I'm now back in university doing my PhD. And gathering up things I sort of found odd, these little smells, and just following them up, in particular ones that are sort of architectural in nature. And so what is this? What are polymorphic write streams, standard object out? Well, a replacement for the Unix standard I/O library, essentially. And what is that? Well, it's an architectural adapter between object orientation, the object-oriented architectural style, and the Unix pipes and filter style. And what we get out of that is significant performance and flexibility benefits. So that's kind of the pitch. And so the overview of the talk, I'm going to introduce the problem a little bit, then I'm going to show it with an example, show you how polymorphic write streams solve that problem, and then present some results. So, introduction. First, what is standard I/O actually, right? We use it every day. Printf hello world is ubiquitous, but it's actually quite an interesting piece of software because it's an architectural adapter. It adapts between the call-return architectural style of the component programming languages, for example, C, and the streaming architectural style, Unix pipes and filters, of the that's used, for example, in the Unix shell. And they're quite different, right? The call and return is synchronous. And it's characterized by completion. You call something with some arguments, and then you return a result, you're done. Whereas in streaming, you don't actually return. You just have some results, you compute something, and you stream it on to the next target. And these don't match, and therefore we have to adapt between them. So I was quite puzzled when I started working in object orientation that all the implementations for talking to the Unix world didn't really do much with the object orientation mechanisms that they had available. All of them were basically, here's some string, here's some bytes, go play with them, and essentially the same level of abstraction as printf or write, which is unsatisfying, first, aesthetically. And second, there's actually some problems, because when you look at the adapters more closely, you notice that when you do some output, they will tend to convert the objects to a string representation with a call, and then take that result, that completed result, and ship it out, which is unfortunate. Because when you have a deeply nested graph, that means the entire graph has to be converted to bytes, has to be serialized, and then shipped out. So you're not streaming anymore. Again, that's unfortunate because one of the reasons we're using the pipe and filter architecture style is that we want to stream. And there are different implementations of this. In what I used was Objective-C, and there's the description method, and again, it just returns a string. Java, if you write something, it'll call toString. In Ruby, it's toStr, and basically most of the languages have some mechanism like that. And again, that's a mismatch, right? Because in streaming, we want to be able to deal with large, unbounded data sets, and we can. And in object orientation, we have polymorphism, and we want to deal with object graphs. But when we put them together, they don't work well together. We can't stream these graphs, and it's hard to produce variations. So here, an example. Let's just get a simple tree, right? So we have as a stand-in for an object graph. And so it has a left-hand side, a right-hand side, and a payload, which is just a string. Nothing special. And when we try to serialize this using the call and return architectural style, we run into some problems. First, the flexibility is just that we want from object orientation just isn't there. And then we get performance problems. And finally, the performance problems in the extreme case turn into stability problems, is that it won't work. First, flexibility. So as we saw before, the message sent to convert those objects to a string representation is usually fixed by the underlying library. And that means we get one representation. What if we want something slightly different? Can't do it, at least not easily, because we don't really have operation inheritance. So if we want, for example, not just a description or an XML description, we have to implement this new method on every object, right? And there's no way of sharing this code. Again, that's somewhat unfortunate. And the other issue is that we at least, in terms of performance, is that we at the very least need a fully serialized representation as a temporary value, not as a final value, but as a temporary value. And that means if we have an object graph, well, we get a complexity of size of the output times the depth of the object graph, potentially. And that essentially is an n-squared complexity. So for example, if the method to serialize into just a debug format this tree, yeah, we do the obvious thing. We return a string that gives the class information about the class, the pointer, and then recursively gives us the left and the right side and the payload. And when we tried to do that with a deeply nested tree, we get some fairly unfortunate performance results. So we vary the depth of the tree from 0 to 1,000, and the output size stays fairly constant because we've constructed the tree specially, of course, knowing what'll happen. So the output size is not quite 12 megabytes. And the intermediate representation goes up to 11 gigabytes, so factor 1,000. That's a lot, and it's definitely not a streaming of this output. And of course, the CPU time also goes up with that. The output, to keep that the units the same, essentially, the output size just hugs the x-axis. And the interesting thing, this is not because there is a deficiency in the implementation. Once we have decided that we will produce the result using call return, we don't have a choice. We will get this kind of performance because the call, when it finishes, has to return a completed result. And when it does this recursively, every intermediate result also has to be completed. So particularly when we know that this is the case, we can construct a graph that is very heavy at the leaves, and then every intermediate result has that size. And we bubble that up, and so we get the n-squared. And of course, once we know that, we can easily make it crash by just introducing a cycle. That'll go boom. Because we have no way of storing existing already traversed nodes. Right? There's just no room. We just get a return. That said, why does everybody use this call return pattern? Well, because it's convenient and it's obvious. It's the obvious thing to do. After all, it's object orientation, right? We write methods that we give arguments to and that return values, despite the fact that the results aren't really what we want them to be. And I call that the gentle tyranny of call and return, because it pulls us in with, hey, this is easy, this is nice, we can do this, and it tempts us to do the wrong thing. And of course, with small data sets, it's not noticeable, or not very noticeable. So how do we solve this? Well, obviously with polymorphic write streams, otherwise I wouldn't be here. And a polymorphic write stream is an object of a class that has sort of three components. First is the very low-level component, which is essentially the equivalent of the Unix standard IO. Write some bytes to the output. And then there's a high-level interface, which is very simple. Please just output this object. And then there's the mechanism in between, and that basically is triple dispatch with chaining. And I'm going to explain what I mean with that. So the low-level interface is defined by a protocol, Java interface. And it's really, the append bytes of length is really all you need. Right? That's sort of the basic. Please put some bytes out. The rest are already somewhat convenience. At the very high level, well, it gets even simpler. Here's an object. Please serialize it. Do something with it. And then we get the dispatch. So first, once the stream receives an object, it does a double dispatch back to the object with the name of the stream in the method. And the default implementation of this method is automatically generated. And obviously, you need some metaprogramming abilities in your language, but here this is probably not much of an issue. And you also need to be able to extend classes at runtime. This is also probably not much of an issue here. But you can also write them manually. And then the object, now, for example, Smalltalk has some streams that go this far with the double dispatch, but then the output stream, once again, has just sort of very basic byte output capabilities. So you encode the actual format that you're outputting to in the object and not in the stream. So we dispatch back to the stream, and now with application-specific protocols. For example, the plist streaming is sort of a basic protocol for things like JSON and next Apple property lists, things like dictionaries, keys, values, arrays, and there's the recursive. Where's the recursive? Yeah. Well, this is essentially the recursive case, write object, but with the convenience of specifying the key. But a different stream can implement, for example, PostScript graphics, right? And then you have some graphics methods. But the same protocol can also be implemented by, for example, PDF stream, and that outputs slightly different code for the same protocol. And that means the same objects. The objects don't actually encode the output format. The streams do. So you can reuse, for example, the same graphical objects with different output streams. In detail, the sequence is the client sends the object to the stream to be output. The stream then calls back to the object. The object encodes itself, potentially recursively, and then at the end you're done. And of course, the stream actually does the byte formatting. As an example, very simple example, that node class that we had before would encode itself like this. It says, well, I'm going to begin, hello stream, begin an object, write my payload, write my left node, write my right node, and I'm done. Right? And the key being that the recursive case does not already encode the object, but actually tells the stream to then recursively encode. And that's the difference. That's the key difference. Message chaining. The root implementation of the method that is implemented on the object side for the stream calls the method on itself with the message of the superstream. And with that, you get a kind of operation inheritance. So an example, we have a JSON stream that's a subclass of a property list stream. And so the default method that is actually, this is usually auto-generated, delegates to the property list stream. And therefore, if I just start with the JSON stream, it is completely compatible with the property list stream. And then I can start modifying it. So I can do programming by difference and just encode some of the small differences, such as the exact format of how is the starting point of a dictionary encoded in JSON versus in a, for example, in an Apple property list. Results. Well, we had 3 problems. Flexibility, that is solved. We can simply subclass a polymorphic write stream and just encode a difference to the superclass, and we'll have the new format defined. Performance, we get real streaming. And finally, well, safety, we can detect cycles because we have an object where we can store the information. And for flexibility, this is part of open source project, MPW Foundation, and there is just a plethora of substreams that are implemented very simply. There's also the PDF PostScript writers, and for example, the PDF file has a graphics component and a structural component. Those are subclasses because they're slightly different. And again, each of these cases would be very onerous to implement from scratch. In terms of performance, on the left is the graph we just saw. On the right is the same thing with the polymorphic write stream implementation. One thing we notice is it's all nice and flat. The other thing I should point out that the units are vastly different. So this is still the same. This is gigabytes of output, so I kept that the same, and the output is bit identical. CPU time here was seconds. Here it's tens of milliseconds. And the memory is essentially constant 7 kilobytes rather than 11 gigabytes of temporary memory. And that's why you want streaming. Again, in terms of stability, yes, you can detect cycles. This is in the paper. I'm not going to show it here. It's fairly trivial. Some observations about these results. First thing is we've gotten rid of the temporary results, the intermediate results. Actually, we can also get rid of the objects completely, right? Because of the stream providing the facilities for encoding at a high level, we can just procedurally encode stuff. Again, this is more noticeable in the PDF and PostScript cases. But of course, this is actually the code to reproduce the node tree without actually instantiating the node tree. But it does the same result. And the question then becomes, well, can we have an object that's actually not instantiated? I find that very interesting. Another observation is that whereas, of course, the implementation of this is in a call return style, but getting proper streaming was quite complex. Polymorphic write streams are not that simple. Going in the other direction is trivial. If I want to do a call return style, that's the wrapper, right? I open the stream, I write something, and I get the result out of the stream. And it's completely generic. I can do this once. And that opens up the question whether maybe the streaming approach is actually the more fundamental one. So if we want to implement things, maybe they should be implemented in a streaming approach with the call return that we usually do on top as a simple adapter. Outlook. Well, we've done standard object out. Obviously, there's standard object in to work on, which is, interestingly enough, I mean, I've started work on it a little bit, and it's completely different, although it then finally seems to come in the same direction. Then there's this maybe somewhat strange notions that the streaming approach may be more fundamental than the call and return approach. And that because we can more easily adapt in that direction than in the other direction. And that then also begs the question of course, right now because it's highly complex, it's not feasible, right? So we would probably need some linguistic support to make that happen. And that's, something to look into. So, and that means I'm done. Quick recap. The polymorphic write streams resolve the mismatch between object orientation and streaming. It means we can get streaming, polymorphism, and complex object graphs to work nicely together and have all the characteristics that they're supposed to have. There's a completely trivial interface. In terms of linguistic support, it might even not make sense to have that as a message send, but rather have maybe special syntax like an assignment. Implementation is triple dispatch with chaining. And in the outlook, again, there seems to be some obvious generalizations we can make and some linguistic support. And the linguistic support is starting to be added into Objective Smalltalk, which is my architecture-oriented programming language. And with that, questions?
Very nice stuff. I'm a compiler guy, and one of the things that this looks to be similar to, especially if you're in this mindset of what is fundamental and you're trying to find similarities and the foundational basic stuff, is pretty printing. Unless you have already looked into it, I haven't read the paper. Maybe you should try to see what kind of things you can learn from them or apply it there. So in pretty printing, there have been some attempts to also raise the level of abstraction beyond, we dump the bytes of whatever structure it is. With like, okay, we have boxes, and I don't know, I want to stay on the same level of indentation now, and so forth. So maybe there are some lessons to be learned. I'm not sure which way. Should we learn from you or you from us? But
ideally both.
Hopefully both, yes. But especially if you're looking for these global big things, then you should probably tie it in there again.
Yeah.
And see what.
Yeah, I mean certainly, for example, the Objective Smalltalk compiler is a stream, which is kind of weird. And I've certainly started using this approach in many places because I know, well, one, I'm starting to find it very simple. And the other part is, of course, I know I don't run into performance explosions later on with larger data sets. Yeah, thank you.
Any other questions? I have one of the things that came to my mind, because but maybe I'm totally off. So you criticize the tyranny of call and return. So I was thinking generators. How do your write stream or streams relate to generators? Then you essentially yield something, and then later you can come back and grab some more.
Yeah. That is an interesting. I mean, so the generators in my mind, also the Unix filters, seem to have this idea that you must have concurrency underneath, even if it's pseudo concurrency, which this shows you don't need because you go passive. I think the generator approach is probably more general, slightly. What I found applying this is that even despite the fact that this is mostly synchronous, I mean, you can add asynchrony if you want to into the approach. It seems, by being mostly passive, it seems to handle most of the situations I put it into. But yeah.
I'm not sure that I see the concurrency necessarily, but I agree. You kind of externalize the iteration part with the generator, so you move that to the client.
Yeah, and here it's a sort of a ping pong, right? The stream and the object graph cooperate in producing the output.